Welcome to this short video on the first part of stoichiometry. Stoichiometry is a process where you can look at a chemical reaction, and through that reaction you can figure out how much product is going to be made. Like if you had, so many grams of hydrogen and so many grams of oxygen, you could figure out what that's going to produce as far as how much water you're going to get out of it. You could figure out the volume of water, you could figure out the mass of the water. The first step here is multimole conversions. It's kind of the beginning stages. So let's keep moving on. Okay, the equation for a turkey sandwich might look like this. 2 turkey plus 1 cheese plus 2 pieces of bread equals 1 turkey sandwich. Now what you should get out of this is that these here, my pen will work, these are the coefficients, and you see those in balanced equations. That's the part that you balance, right? That you're trying to figure out how much of each reactant, turkey, cheese, and bread, is needed to produce a product, right, which is on the other side of this arrow here. So you need 2 turkey, 1 cheese, 2 bread to make the product of a turkey sandwich to make one of them. So what you can see here is that you can use those values to try to predict what's going to happen at the end. If you want to make 2 turkey sandwiches, what do you need? Well, you need 4 slices of turkey, you need 2 pieces of cheese, and you need 4 slices of bread. This is all we're talking about when we're talking about mole-to-mole ratios. It's that simple when looking at a chemical reaction. So the coefficients in the balanced chemical reaction show relative number of moles of each substance. Right? So that's what the coefficients are, and we're going to be converting from moles of one substance to moles to another. In other words, it's telling you the ratio of moles. Okay, you can have more or less than the value given, but they're still in the same proportion. So you don't have to have 1 full mole. You can have 2.3 moles, and then you'll figure out how much that 2.3 moles converts through the reaction. And it'll make more sense when we start looking at the reactions. So if you know the actual number of moles of one of the substances in a balanced equation, you can determine the number of moles of the other substance too using the mole ratio. So let's look at an example, and I think you'll see it's going to make sense, and it's fairly simple. So if you take this chemical reaction, right, NH4NO3, it's going to produce, right, or it's going to decompose into N2O and H2O. Well, that's not a balanced equation, right? So we need to balance this equation first. Let's see if we can get to that part. There we go. So now we have a balanced equation, and the question asks, you have 4.2 moles of NH4NO3 reacting. How many moles of H2O are produced? So you're going to use these mole-to-mole relationships to figure it out. If you look at NH4NO3, right, there's nothing here, so it's understood that there's a 1 for the coefficient there, and we're trying to get to the product of water, so there's a 1 to 2 mole ratio. So what that tells you is that for every 1 mole of NH4NO3, when it decomposes, it's going to make 2 moles of water. So using this in a formula, right, if there's 4.2 moles of NH4NO3, because we want the moles of NH4NO3 to cancel, and so it becomes important to write the name of the substance, not just that 1 mole like we were doing in the last chapter. So now we have 1 mole of NH4NO3, and you're going to use that mole ratio. Well, if you have 1 mole of NH4NO3, it makes 2 moles of water. So now your units are going to cancel out, right, your of NH4NO3, and your unit of moles is going to cancel out, leaving you with the units of moles of H2O. So 4.2 times 2 gives you 8.4 moles of water. Let's look at another one. So how many moles of N2O are produced? Well, if you go back and you look at that equation, right, that balanced equation, for every 1 mole of NH4NO3, there was only 1 mole of N2O2. So, again, putting the moles of NH4NO3 in the bottom so that the units cancel, using the mole-to-mole relationship from the equation, right, it was a 1-to-1 relationship using those coefficients, you're going to get 4.2 moles of N2O2. Next problem, we have hydrochloric acid is reacting with zinc, right? And it is a single replacement reaction, and it produces zinc chloride and hydrogen, a hydrogen gas. So we want to know how many moles of hydrochloric acid are needed to react with 2.3 moles of zinc. So before we can do it, we've got to figure out the mole-to-mole relationship. Therefore, we need to figure out what we need to have a balanced equation. So balancing the equation, right, we have 2 moles of HCl react with 1 mole of zinc, right, to produce our zinc chloride and our hydrogen gas. So the mole-to-mole relationship between the reactants, I need 2 moles of HCl for every 1 mole of zinc. That's like saying I needed 2 pieces of turkey for every 1 piece of cheese to make a sandwich. So how many moles of hydrochloric acid are needed to react with 2.3 moles of zinc? We have 2.3 moles of zinc. We want the units of moles of zinc to cancel. So the mole-to-mole ratio for zinc is on the bottom, right? 1. And then we want to get to the hydrochloric acid. 2 moles of hydrochloric acid are needed with every 1 mole of zinc. So 2.3 times 2 gives us 4.6 moles of hydrochloric acid. So we need 4.6 moles of hydrochloric acid if we have 2.3 moles of zinc, so that we use all of the reactants. Okay, last problem. We've got this C6H12O6 reacts with oxygen gas, and it produces carbon dioxide and water. Right? This is a typical combustion reaction. So if 3.2 moles of CO2 react, how many moles of C6H12O6 react? So looking at this, right, we need our balanced equation. So now that we have it balanced, we have our mole-to-mole relationship. Remember this, understood that this is a 1. So if we have 3.2 moles of CO2, we want those units to cancel. So looking at our equation, we've got 6 moles of CO2. We want to get to how many moles of C6H12O6, so that's going to go on the top. You can see there's only 1 mole needed for that. So there's 1 mole of C6H12O6 needed for every 6 moles of carbon dioxide that are going to be produced. Because it's on the bottom of the equation, right, you do 3.2 times 1, and then it's on the bottom of the fraction, so you divide by 6. So 3.2 divided by 6 gets you 0.533 moles of C6H12O6. And again, notice for sig figs, right, this is 3 sig figs because this value here is 3 sig figs. Let's go back real quick and look at the other ones just for the sig figs again. Looking here, 2 significant figures, so your answer has 2 significant figures. The number of significant figures is always based off of that beginning value. Hopefully this helps with your homework. Let me know if you have any questions.